not to be quiet. Okay.
Nine.
All right, is it on?
Yes.
Okay, good. Okay, welcome everyone to Michael Green's PhD defense. We have the honor today of having Mike defend his thesis. The order of the day is that Mike will present his work. This will be a 40 to 45 minute, 40 minute talk.
I'm clocking myself around there.
Right, where he will give like a summary of what he's been up to during the last almost 6 years, including more than 10 papers that are part of the thesis. And then after this, we will have public questions where everybody in this room or everybody on Zoom can ask questions and have them answered, commented on by Mike himself. After this, at which point we probably reached about 1 hour mark, we will usher everyone except me and Mike out of the room. And then we will have, and also people who are not on the committee out of Zoom. And then we will have the closed session where the committee will
grill, deep fry.
Yeah, grill, deep fry, ask questions to Mike. And the rest of you will be finishing up the food over in the lab.
I promise to do my part.
Good. And after that, we will, before the 2 hour mark, we will have reached a conclusion and we will announce our verdict. The committee is myself, Julian Tegelius, New York University, advisor. Gillian Smith, Worcester Polytechnic, Michael Matias, University of California, Santa Cruz, and Andy Nealon, University of Southern California. And they have graciously agreed, and we are very happy to have them here to sort of comment on and sort of inquire on Mike's work.
Yes.
Orders of the day is that this is an optional event, so Mike will be talking without a mask. I will probably wear a mask when I'm not talking. But that's also you can feel free to not wear a mask when you're eating and so on. Anything I forgot?
I think that's it.
Great.
Awesome. All right, let me share my screen and I'm going to do the classic, can everyone see my screen? Kind of have to ask that. Can everyone see my screen?
Yes.
Perfect. Perfect. Okay, so for this, just in case nobody accidentally clicks the unmute button, maybe we can mute everybody now if that's okay. So if you're not muted, please feel free to mute yourself. Okay, taking this in, guys. I've done this a lot to an empty room. This is a lot different. There's a lot of you. So I guess my name is Michael Cerny Green. I'm going to be giving a talk on my thesis topic, which is automated video game tutorial generation. I want to thank you all for coming. If you're in person, some of you flew in, so thank you very much for flying in. I hope you had a nice trip. Some of you joining us from Zoom. We have people joining us all the way from Malta and California and everywhere in between. So we have a lot of folks from all over the world coming in and watching this. My family is here as well, so hi family. Let's get to it. So automated video game tutorial generation.
You want to unclick the professional audio thing?
Oh, yes. You don't want to set up professional audio?
Just click
Thanks. So part of my committee, Professor Julian Tegelius at NYU, Professor Gillian Smith from WPI, Professor Andy Nealon from USC, and Professor Michael Matias from UCSC. I want to thank you all for, of course, taking part. These are 4 of the busiest people I know. So it was amazing that we got their schedules to line up on a day in June, especially when so many have so many young kids right now in particular. So thank you so much for joining. Oops. My thesis statement that I'm going to try to prove to you guys today is that we can automatically generate tutorials and tutorial levels for video games using mechanics and play personas. And we're going to get into how we're going to do this, where those mechanics are coming from, and how we're going to use play personas to generate these tutorials. But before we get into that, I'd want to get a couple of definitions out of the way. The first is, what is a tutorial? What are we going to be generating? A tutorial is that thing that you typically first encounter when you play a game. It teaches you how to play, right? It's engaging to make you want to keep playing, and it can come in a lot of different forms. You have a bunch of different examples here. You can have it be in-game, such as in Civilization 6 or in Gauntlet, or it can be even outside of the game as part of like a written booklet. It can be written on an arcade machine itself. It can come in the form of pictures. It can be a level. It can just be text. But ultimately, what tutorials do is they teach game mechanics. And a game mechanic, as defined by Miguel Sicart in game design literature, is any event in the game that involves game entities and changes the game state. We're going to be revisiting and talking about a lot about game mechanics. So remember this definition: any event in the game that involves game entities and changes the game state. We're going to be talking about 3 different types of tutorials that we're going to focus on generating. There are instructions, demonstrations, and interactive experiences. Instructions are text-based, right? They give you advice or an explanation into what you're supposed to be doing in play. Like, for example, in Civilization 6, there's an advisor that'll pop up every once in a while that'll kind of tell you, hey, you should build some neighborhoods because your population is growing, or they'll give you advice about what technologies to research. There are demonstrations, which are different than tutorials because instead of being text-based, they're a visual. Like something is playing the game for you. You're not actually doing this. You're being shown what is going to go on. They help you visualize different player actions. Like, for example, in the Pac-Man start screen, before you start playing, you'll see Pac-Man going around and chewing up pellets. And I think you actually eat a ghost in this screen too. So you get to see examples of a bunch of different game mechanics. And the last type, and my personal favorite, are interactive experiences. So these are like levels or challenges that you'll play. And through playing them, through beating them, they will teach you a skill or help you better master a skill that you've already learned. And they'll give you a bunch of different practice opportunities to engage with. So like in Breath of the Wild, there are these temples that early on in the game will introduce core game mechanics to you. And then over time, later and later on temples will give you more complex patterns of these different mechanics, sometimes merging multiple mechanics in a combination to give you more of a challenge. So imagine for a second what a tutorial generator would look like. We'd want it to be able to output these 3 different types of tutorials: instructions, demonstrations, and these interactive experiences. But what kind of input would you need for this kind of a system? Well, tutorials teach game mechanics. So you'd probably want game mechanics to go into this little black box tutorial generator, and it would output these different types of tutorials. But where is this list going to come from? If we're manually giving it to a tutorial generator, that's kind of breaking the premise of automated tutorial generation, right? So we need a way to automatically find this list of game mechanics. You can also indirectly teach mechanics by teaching or encouraging or discouraging certain play behaviors, which we're going to call play personas. For example, if a player is playing really aggressively and they're losing a lot, we could give them tutorials that encourage maybe a more passive or defensive behavior. But how are you going to automatically identify how a particular player is playing, right? If you're going to want to give a player a tutorial that's personalized for them, you need to know a bit about them to make it personal. That's the whole point. So these questions, how are we going to find game mechanics and how do we identify play personas, are going to begin and end my presentation today. This is a list of the 5 thesis contributions that we're going to talk about. We're going to start with how we can find mechanics. Then we're going to talk about how you can generate tutorials using mechanics and personas. And then we're going to end with a way to automatically classify player behavior. And this is going to be our roadmap. So we're going to start up here in the upper right-hand corner with game mechanics and play trace information. We just introduced what game mechanics are. We're then going to talk about mechanic graphs and critical mechanic discovery. Mechanic discovery is one method of mechanics to teach within tutorials. Mechanic graphs are an abstraction that are going to help us search mechanic spaces. Game mechanic alignment theory is a framework through which we can observe mechanics in regards to the environment and the player. And it's another way that we'll be able to extract mechanics from games in order to teach within tutorials. Then we're going to talk about a system for tutorial card generation. Tutorial cards are these accessible systems that display instruction and demonstration-based tutorials. And we're going to review a system that allows us to do that called the Adelphi system. Then we're going to get into the level generation side of this thesis. We're going to first talk about mechanic-dependent scene generation. Mechanic-dependent scenes are these mini levels that scope mechanic use into an encapsulated experience. Then we're going to talk about how we can take these mini levels or scenes and concatenate them together into longer, fuller levels that'll allow a player to practice the same set of skills or similar patterns over and over and over again. And then we're going to talk about a different form of level generation called persona-driven scene generation, where persona-dependent scenes are mini levels which scope a set of player behavioral patterns into an encapsulated experience. And lastly, we're going to talk about a way where we can automatically identify play personas for a persona-dependent scene generation pipeline. That's a lot of contributions. Overall, this was done over 10 peer-reviewed and published papers, and that actually represents less than half of my published record over my 6 years at NYU. A lot of stuff didn't make this list, and that's okay. So I'm going to invite all of you to the other thesis defense next week. Just kidding. I'm kidding. Committee, that's a joke. You guys don't have to go to that.
We're laughing.
Yeah. I hope I didn't get a glare. I can't actually see you guys. Let me first draw your attention to the list of mechanics highlighted now in orange. This list of mechanics are the list of mechanics that we want to extract for tutorial generation. We talked about this before. How do we find these game mechanics to feed to a tutorial generator? Let's first talk about some ways to find this, starting with mechanic graphs and critical mechanic discovery. So earlier we defined a game mechanic. I told you all to remember this. Earlier we defined a game mechanic as any event in the game that involves game entities and changes the game state. But what makes a mechanic critical is that it must be triggered to win the level, meaning that every winning playthrough must contain the set of critical mechanics. We need a way to think about mechanics in order to search mechanic spaces. Mechanics are these events that involve game entities. So let's make a sprite, an entity node. Let's make it blue. That's a nice color, a little blue circle. That's going to represent our game entities. Gray diamond nodes can represent the conditions that involve these game entities. So if something happens, that would be the condition, that if something happens. And then we can have these action nodes that represent the thing that occurs if the condition is met. Nodes can be associated with each other to form a mechanic, like in Space Invaders. If a laser and an asteroid collide, you blow up the asteroid, right? That's a pretty simple way to represent the game mechanic using atomic interactions. That's what we're going to call this concept. When we associate mechanics together, we can create mechanic graphs where, because they can share these game entities, they're not exclusive to a particular mechanic. One mechanic's output can be the input to another mechanic. So how do you search for these critical mechanics? Well, you'd start from the mechanics that a player can trigger directly, things like swinging a sword or jumping or collecting a coin or colliding with something. And then something happens, right? This number 2. And then you have your list of critical mechanics. So we're going to introduce over the next couple slides 2 different ways that you can find this. The first is with uninformed discovery. We're going to use a really simple game coming from the general video game artificial intelligence framework called Zelda. A lot of you in this room and maybe on Zoom are familiar with the GBGAI framework. I'm not going to get into it too much right now. But Zelda is a tiny dungeon crawler where you need to get to a key and unlock a door to win. You want to avoid monsters, but if they come too close to you, you can swing a sword and delete them. So grab key, go to door. If we use an uninformed discovery method like breadth first search here, where we're just searching from a player starting action to a winning terminal condition, you can easily see how we get pick up key, unlock door, win. Very simple, right? So breadth first search and uninformed discovery works well here. But if we were to take a more complex game like Plants vs. Zombies from the GBGAI framework, this is a tower defense game where the goal is to survive for a certain amount of time, in this case, 1,000 game ticks. And you defend your base from zombies by building these little plants that will shoot pellets and or peas, and these peas will destroy enemy zombies. The problem is that if we use uninformed discovery here, we're going to miss most of the important mechanics in the game, right? You basically are told, oh, just live to 1,000 game ticks, but you're not told how to live to 1,000 game ticks. What are you supposed to do in order to make sure that that happens? So this isn't good enough. We need something better. And that's where uninformed discovery comes in. So rather, before we were using an uninformed tree search algorithm like breadth first search, here we're going to be using informed tree search algorithm like best first search using heuristics. But first we need to assign costs to our nodes in order to use a heuristic search algorithm. So first we'll have an agent play a game a couple dozen times, a couple 100 dozen times, however much you want. We then look for a single play trace, which has the least amount of unique mechanics and in which the agent won. So it has to be a winning play trace with the fewest amount of unique mechanics. And then we inject the first occurrence of each unique mechanic into our graph as the cost of the node. And then we could use an uninformed search like best first search to power their way to the winning mechanic. So in this particular case, we're using a minimum cost and a priority queue. So let's walk through how that works. The rules are really, really simple for informed search. You basically have to choose the lowest cost node at every moment in time in your queue, which we've highlighted in yellow. And you can't go backwards in time. So we'll show an example of what that means. So first we have a choice between frame 75 and 1000. Frame 75 is of course less than 1000. Then we have a choice between 95, 105, and 1000. We're going to pick 95. We can't pick P hits tombstone because that never happens in our play trace. That's why it has a dash. So our choices are 200, 105, and 1000. We're going to pick the 105. Then we're going to pick the 200. Now we can't go backwards in time and pick 80, even though 80 is less than 1,000. So we're only left with time reaches 1,000 game ticks and you win the game. And this would be the critical mechanics of Plants vs. Zombies, which is a much better way of capturing than our uninformed method before. So how do you evaluate these methods, right? How do you know if you're picking the right mechanics? Well, we tried two different ways to do this in this research. The first was to use agents. The theory was if you know about the critical mechanics, you have an advantage in the game. You're going to get more points. You're going to win more. And so what we did was we took a bunch of Monte Carlo tree search agents and we injected mechanic information into the agents themselves. We rewarded them anytime that a critical mechanic showed up. And you can see we have 4 different agent types that we played with. We had a baseline agent that knew nothing. It was just Monte Carlo tree search, just plain. We had one where we gave it the uninformed critical mechanics. We had an informed critical mechanic agent. And then we had an agent where we gave it all the mechanics in the game, regardless if they were critical or not. And we did this on 4 different games in the GBG-AI framework of varying complexity. On the right-hand side, you see the average scores by agent. That doesn't really tell us much. So it looks like that our theory about, well, you'll get a higher score doesn't really hold up here. It looks like, for the most part, if you don't give it any mechanics at all, you actually perform on par with a lot of the critical mechanic discovery agents. But our win rates are vastly improved if you give it information about the critical mechanics, particularly for a game like Zelda. Now, Solar Fox, we weren't really seeing a lot of changes, but in Plants, you'll see that even if we give it the uninformed critical mechanics, that doesn't help it win more because that was only time reaches 1,000, right? We went over that example. But the informed mechanic search does help us win more, as well as just giving it all the mechanics in the game. Now, the informed search method did give us most of the mechanics in the game, so there's not that much difference between the all and the informed on that game. But you can see that the informed on a whole, on average, across these different games seems to be better than no mechanics or all mechanics. And it certainly seems better than uninformed. But that doesn't necessarily mean that this is the only way we should evaluate these methods. We should also ask people, because tutorials are meant to be consumed by people. So we went out, we made a big user study, and we asked a bunch of people, what do you think is important to know after playing these games? And it turns out that the informed search method matches at a much, much higher rate for more complex games like Plants and Real Portals than the uninformed method does. Now let's get back to this graph. We've seen how to get mechanics from mechanic discovery. Let's look at another method for mechanic extraction for tutorial generation. Up to this point, we've defined critical mechanics as those required to win, and we demonstrated how we can discover these critical mechanics using these methods. But player enjoyment shouldn't be limited to just winning and losing. That's very binary, right? We don't just play games to win. We play games to have fun. And because people are different, and we engage games with their own biases and motivations and goals, that impacts the enjoyment that we receive from play. So we need a framework through which we can think about different players playing games differently and what may be important for them to know about for a personalized tutorial. So let's envision the intersection of the player and the system. On the X, we'll think about the system, right? We'll put systemic reward. So these are things that like you get points or you get more agency or you win more. That'll be on the right. And on the left, we're going to think about systemic penalties. So these are things that take away points or take away lives or take away agency or you just outright lose the game. On the Y-axis, we're going to plot agential influences for this mechanic. How much does a specific player want to trigger or avoid triggering this mechanic? And it's going to be different for different people, right? So if higher up on this in the Y means that you want to trigger it more, and down means you want to avoid it. And this intersection creates 4 quadrants. Notice how on the rightmost side, we have our critical mechanic dot right there. Those would be the mechanics that would be critical in the game. And then on the left, we have fatal mechanics. Those would be the mechanics that will just outright kill you. On the top, we have our highest incentive mechanics. Those are the ones that the player really wants to do. And on the lowest, we have our avoidance mechanics. Those are the ones that the player does not want to perform. In quadrant 1, we'll have mechanics where the player will reward you for them and the player wants to trigger. In quadrant 2, that will be the mechanics that the game punishes you for, but the player wants to perform regardless. In quadrant 3, we have mechanics that the game penalizes you for and you don't want to do. And in quadrant 4 are mechanics that the system will reward you for, but the player does not want to do. All right. So if you're on the Y equals X line, that would be in alignment where the game and your own incentives are in alignment with each other. And if your Y equals negative X, then that means that you're out of alignment. And this isn't really like a statement on what's correct behavior in the game, right? You can be out of alignment and be running counter to what the system is rewarding or penalizing you for. And that's okay. That's not really a judgment there. So let's look at this for a popular game like Super Mario. Everyone probably knows what Super Mario is. I'm hoping. I can't see Zoom, but I'm also hoping that you guys are familiar. Super Mario is a two-dimensional platformer game. You want to touch the flag at the rightmost part of the level to win. You want to avoid losing lives. And along the way, you jump a lot and you run your way through the level to collect power-ups and coins. So we're going to look at two different players here. We're looking at an explorer player and a speedrunner player, which is the circle. An explorer player would be like a casual Mario player, someone who's just like playing Mario, having a good time, not really in a rush to do anything. A speedrunner, on the other hand, is someone who's trying to race through the Mario level as fast as possible, right? So they have a couple of shared incentives. The first one is that they probably care about winning about the same amount, right? So they both want to touch the flag and they want to move to the right because that will allow them to win. And they probably care about losing about the same amount. They probably both don't want to lose. So they are going to try to avoid losing lives. But there are a couple of key differences between these two players. The first is with running. A speedrunner is going to want to run more than an explorer player because that allows them to get to the level exit faster. And an explorer will probably want to collect more coins because that is an aesthetically pleasing thing to do inside of Mario, and it satisfies that curiosity. So I want to bring a quick concept into here called mechanic frequency. We're going to use this term quite a bit for the rest of the thesis. It's the number of times that a mechanic is triggered within a single session or level. You can use mechanic frequency in order to automatically estimate game mechanic scores or values. So this is the only math that's in the entire presentation, I promise. It's not the only math that's in the thesis, unfortunately, for the thesis committee, I'm sorry. But it is the only math that's in this presentation. It's really simple. It's a distribution distance calculation, right? And then there's some sign stuff going on in there too. What you want to do is you want to find the distribution with the condition that you want, be that winning or a particular player. And you're going to look at, for the given mechanic that you're looking for, the amount of times that that mechanic is triggered, the frequency of that mechanic. You want to calculate the distance between the conditional distribution and the overall distribution. And then you want to take the sign by finding the sign of the difference of means, right? So if you wanted to calculate for systemic GMA, so the x-axis, you take your winning or your losing distribution, you find the distance between that distribution and the overall, and then you take the sign of the difference of means and you multiply those together, and that's your systemic reward or penalty for that mechanic. And then if you wanted to do it for the y-axis, you take a player distribution. So for example, Julian's play traces, right? And how many times he collects coins, and you compare that against how much everybody else collects coins, and that's going to be his score for coin collection. And then, of course, I would have a different score, and Graham would have a different score, and so on and so forth. So we're going to use a framework called Mini Dungeons 2 in order to test out theories of game mechanic alignment. We actually have some data here that we can play with this on. Mini Dungeons 2 is a research game. It's a two-dimensional roguelike dungeon crawler. You're this little gray hero that's moving around the level. That's me playing. And you can collect treasure chests and you can kill monsters, you can drink potions, and then there's this little minotaur that'll follow you around, and you can throw a javelin once in order to do damage to monsters, and then you have to go pick it up. Otherwise, when you run into monsters, you'll do damage to them, but they'll do damage to you. There's three different pure play styles in mini dungeons that we're going to focus on here. Three different types of players. There are runners who speed run through the level and try to get to the level exit as fast as they can. There are treasure collectors who try to collect all the treasure in the level before trying to win it. And there are monster killers who try to slay all the monsters in the level before trying to win it. We collected a data set of Mini Dungeons 2 players. Some of the people in Zoom and some of the people here in this room were probably parts of that data set. So thank you for participating, if that was you. We had 363 human players for a total of 853 unique play traces. And we tracked what mechanics were triggered and how many times they were triggered in each play trace. And then we labeled the traces using a process called action agreement ratios. I'm not going to go into that process right now. That's all in this thesis right here. But just know that it's a lengthy process. For the 853 play traces that we labeled, it took about 7.5 hours to label them all. Okay. So we calculated the Y values for each of these different combinations. Oh yeah, I forgot to mention these three play styles can be combined. You can be hybrid versions of different play styles. I should have mentioned that. And then there's also a sizable distribution of players who weren't labeled by anything because they didn't play like any of the three play styles, which is really, really a cool, interesting finding that we talk about in the thesis. So we look at 6 different mechanics here. We're going to look at enemy kill, take turn, use portal, collect treasure, collect javelin and collect potion and javelin throw, those kind of make sense what they do. I think you can figure out what those mechanics are doing. And we're going to look at all these different labels. And we calculate the Y values in GMA for each of these personas. But if you remember, now that we have these numbers, we want a list of mechanics, not just a bunch of numbers, right? Game mechanic alignment, just the number value isn't going to give us a list of mechanics. So how are we going to turn this into a list of mechanics for each of these different personas if we wanted to build a tutorial for a given persona? And the answer is we can just rank them. So we take the magnitude of their vector, and that is the more important mechanics are the ones that are the larger magnitudes. And then we're going to look at negative values are just grayed out. So those are things that like I don't want to perform, and the white values are the positives. I want to perform these things. So let's look at the runner really quick. So a runner, again, it's a speed runner who just wants to race their way through the level. If we were to read this, it would tell us that the runner does not want to collect potions, does not want to collect treasures, does not want to take a lot of turns, doesn't want to kill a lot of enemies, throw javelins, or use portals. Well, if you want to win mini dungeons too, there's really only one other thing to do. And that's just to get to the exit as fast as possible to avoid doing any of these things, right? Which is what we think a runner should be doing. So this is really cool that this validates what the users are also performing when they're labeled as runners. And then if we look at treasure collectors want to collect treasure. They want to take a lot of turns and take their time to collect these treasures. They want to collect potions. They want to kill enemies. They want to throw javelins, and they want to use portals, right? So treasure collectors kind of want to do a mix of everything, so that way they can get around the map and collect treasures. And it may involve killing some enemies to do so. So if we wanted to then build tutorials for a treasure collector, we probably want to tell them about these mechanics. You want to do these things as compared to a runner who does not want to do these things. And now we have all this information for every single type of persona available to us in this framework. Now let's get back to this graph. We've now seen how we can get mechanics from both mechanic discovery and game mechanic alignment. So now let's look at if you remember at the point of this thesis, let's get into how we can generate tutorials. We identified 3 different types of tutorials that we want to generate: instructions, demonstrations, and interactive experiences. Now we're going to talk about how we can take a list of these mechanics and generate instructions and demonstrations with them. And we're going to do this using the Adelphi system. Now, this has a different slide background than everything else because this is ruins of the Oracle at Delphi. I am a history buff. The Adelphi system was named after the Oracle at Delphi, which stands for automatically designing legible full instructions for video games. So the Oracle at Delphi was a mythological place. I think it's a real place, but in myth, it was a place where you could go and get advice of how to proceed, how you're supposed to move on in the future, kind of what a tutorial does. So how the Adelphi system works, it's really, really simple. It can take a list of game mechanics, and it can also take an optional set of frames where mechanics have occurred, right? And it can build a tutorial card for that particular game. So I want to show this off to you. Here we are. So we took games from the GVGAI framework, okay? And we use the uninformed critical mechanic discovery method to find these to find these game mechanics. And so this is Zelda. Remember when I was showing you Zelda before? Collect the key, go to the door, you win the game. That's what this is describing to you right now, except the difference is that rather than looking at the raw mechanic values, you're actually reading English, right? English sentences, and you're seeing a demonstration of Zelda collecting a key, going to a door, and then you win the game. It also gives you some other information like who you are, which is also automatically parsed from the game rule set, some information about how to do movement and controls, and then we added a little bit about fatal mechanics and getting points. All of this stuff is automatically found and generated, except for the layout of the card. That was actually hard-coded. But everything else, all the content that's in here is found automatically. Now, how it transforms game rules into English, we use a very simple grammar transformation tree. So, for example, we check first if a mechanic is a terminal mechanic, whether you win or lose if it's triggered. If it's not, then it checks to see if there's 2 sprites involved. If it's a kill sprite mechanic and there's 2 sprites involved, then it'll say something like, if object 1 and object 2 collide, object 1 will be destroyed or opened or collected. And so that's basically what the tree structure is like. We talk about this more in the thesis itself, but you can see now that you can take various game mechanics and transform them into simple English sentences and show a demonstration of what that mechanic is doing. So now that we have our list of game mechanics and we've shown you how to do instruction generation and demonstration, I think it's important to add that it doesn't just have to come, this list of game mechanics doesn't just have to come from uninformed mechanic discovery. It could come from game mechanic alignment, the way that we just showed you before. It could also come from informed mechanic discovery, which we haven't actually tried out in this work. So now that we talked about instruction and demonstration generation, how do we generate experiences? Experiences are a little bit harder. You engage with them, you don't read them, and you don't watch them like instructions and demonstrations, right? They're a little more elusive to capture. So we're going to move on to the level generation section of this graph, and we're going to start by talking about mechanic-dependent scene generation. And to do this, we're going to talk about Mario. We're going to switch over to the Mario AI framework for a minute. Now, we're going to be generating scenes. I think it's important for me to then tell you what a scene is. A scene is a level in a video game, but it's very small, and it contains an experience, like a single or maybe like 2 experiences, but not a lot's going on in a scene, okay? It's very encapsulated. Like, for example, this is a scene in Mario that shows that you have to jump, right? In order to get through this scene, you have to jump from the first pyramid over to the second pyramid. It could also involve things like slaying a specific enemy or collecting a coin or getting a power-up. But you can imagine that a Mario level is made up of a lot of these things, right? Kind of stacked next to each other. Mechanic-dependent scenes are scenes that promote the use of a specific mechanic or specific mechanics. It scopes mechanic use into a small experience, and you can use any list of mechanics in order to target. To generate these scenes automatically, we're going to be using an algorithm called MapElites. MapElites is a quality diversity algorithm that allows us to evolve high fitness solutions and organizes them based off of behavioral characteristics. In our case, the performance, which is our y-axis here on our figure B, is simplicity. We're trying to make tutorial levels, so these scenes are going to be as simple as possible, right? Not a lot of noise, not a lot of clutter, just the mechanic, and that's it. And we're going to be using mechanic activation as our behavioral characteristics. So these feature 1s and feature 2s are going to allow us to build a grid of whether, which mechanics were triggered in the scene by an agent playing them or not. The evolutionary process is quite simple, right? We have an agent that plays a generated scene, and we track the fitness function for that scene. And we also track which mechanics are triggered by that agent while it was playing that scene. And when we let evolution run for a little bit, we get something like this. So this is in the Super Mario framework. This is an example of 2 behavioral characteristic mechanics, stomping on an enemy and collecting a coin. And this can make 4 distinct cells, right? We have a coin and a stomp, which is the upper right-hand corner. He collects the coin like very early in that scene. You just barely see it at the beginning. You have coin and no stomping. You have no coin and no stomping. And you have no coin with stomping. And you can see we can have different combinations for all of these different dimensions that we talk about. We have a few different ways of jumping in Mario that we're tracking, different ways that you can kill or stomp on enemies, different ways that different objects that you can collect, like mushrooms and coins, that'll have different effects on your character. But a Mario level is much bigger than a scene. Now that we have a collection of these scenes, let's talk about how we can build full Mario levels with them. And we're going to do this by imagine a situation where we want to practice a set of mechanics, but we don't want to play the same level over and over and over again. Okay, I'm trying to build a motivation for this here. We would want a new level, which is mechanically analogous to the old one. Sequential generation is the process of taking scenes and concatenating them together. When you do this, you can build sequential level curriculums from scenes. Theoretically, these scenes could come from anywhere. And for now, we're going to use the mechanic-dependent scenes. And you can give these players sequences of opportunities to learn sets of game mechanics over and over and over again without making them bored of that original level, right? So if we look at a Mario level in terms of the scenes, we mentioned this briefly before, it'll look something like this, where the black lines will delineate where one scene ends and the next one begins, and we can chain them together using simple concatenation in order to connect them. So unlike mechanic-dependent scene generation, the evolution process for sequential level generation uses single objective evolution. So the object is to match some input mechanic sequence. First, you have an agent play a level, let's say World 1-1, the very first level in Super Mario. Then you stitch together some scenes, and then you have that same agent play that stitched level and see how closely the mechanic sequence matches up. It does not use behavioral characteristics like scene generation. So don't think about quality diversity anymore. It's just single objective. So you can see here how we could have missed mechanics where, say, I was supposed to do a long jump in between that high jump and Goomba kill, but I didn't, right? I just went straight to a Goomba kill. Or I can have extra mechanics where I did a Goomba kill and a high jump and a long jump where I wasn't supposed to do any high jump. And that'll count against your fitness. When we let evolution run for a little bit, we end up with these kind of results. So on the left-hand side, we have the original World 1-1 Mario level. And on the right-hand side, we have a generated version of World 1-1 that was stitched together using this process. Now, this generated level is not a 100% replica of the World 1-1 mechanics, but it does contain every mechanic in the correct order for World 1-1, with the exception that it has some extra mechanics spaced in there. Now that we've seen how we can take a list of mechanics and generate levels which showcase those mechanics, we're now going to talk about a different kind of level generation using personas. And to do this, we're going to revisit the Mini Dungeons 2 framework. See, we go in circles a lot in this presentation, kind of jump around frameworks. We're going to take advantage of the personas that already exist in this game that we talked about, the runners, the treasure collectors, and the monster killers. So I want you to remember that mechanic-dependent scenes are those scenes that encapsulate mechanic experiences. Persona-dependent scenes scope playstyle behavior into an experience. So we can use any list of procedural personas, which are artificial models of player behavior that act like an archetypal player would. So if we have a runner agent that can act like a human runner, that is a procedural persona. The evolutionary process is similar to mechanic-dependent scene generation. So instead of using one agent that plays a level and tracks what mechanics are being triggered, we're going to have three different personas, three different procedural models to play these levels. The fitness, like before, is simplicity. And the behavioral characteristics this time are the persona health. So how does the runner end the game versus the treasure collector versus the monster killer? Now let's look at some results. We're going to look at balanced levels and unbalanced levels when we're looking at these results. Balanced levels are where all personas end the level with a similar amount of health. On the left, everybody, no matter how they're going to play this level, is going to end the level with the same amount of health. There's nothing that can damage you in this, right? There's only really one thing to do, which is go straight to the exit, unless you just want to run circles around the map. And on the right-hand side, we have a similar but opposite version of that, which is a balanced level in which no matter what you do, you will lose. This level's unbeatable, right? No matter how you act as a persona, you're going to die. So you're not going to be able to beat this. Unbalanced levels are where one or two personas have much different health values than the others after play. Sometimes these levels are outright unbeatable for some personas while being relatively easy for others to beat. Here's an example of a challenging level for a treasure collector and a monster killer persona. If you were a runner, you could simply just go straight to the exit. The runner's in green, right? If you're a treasure collector, you'd go down and get that treasure, but you have to be careful. There's a trap right next to the treasure that you don't want to walk over. And this ogre is probably going to come over and try to bruise you up, right? And try to take that treasure for himself. Or as soon as he sees you, he's going to become enraged and go after you. If you're a monster killer, you're going to want to kill these two ogres, but ogres can be a little bit tanky. So they're going to probably bruise you up when you're trying to take them down. They have lots of hit points and they can do a lot of damage to you. Now, in this instance, you probably wouldn't want to just play as a pure treasure collector, right? Because if you were to go straight for that treasure, that wizard would be blasting you with fireballs the whole time, right? So it's trying to dissuade you from being a treasure collector by maybe, if you want to go for that treasure, first throw a javelin at that wizard to take them out, and then you can go for the treasure safely. Or be a runner and just go straight to the exit because that's actually relatively safe because you get behind a wall and now you're out of sight. In this level, this is heavily skewed. This is a very unbalanced level against treasure collectors. It's a more extreme version of the level that we just saw, where if you're a treasure collector, you're going to get blasted to smithereens by those two wizards. There is no way that you can beat this as a pure treasure collector without first taking out some of those enemies as a monster killer. So it'll force you to play as a monster killer before you go for that treasure. And you have to be kind of clever about the way that you are a monster killer because you have to use a javelin to take out one of these ranged enemies before they nuke your health. Or you could just be a runner and you can quickly go up to the exit. Again, very easy level for a runner to beat. And that's how you can generate tutorial levels using personas. Now, let's say we wanted to put this into a pipeline. We have a player play some levels. We then feed them more levels based off of how they play. How can we get who they are? How can we understand how they're playing without straight up, I guess, asking them, who are you? Which actually we had some research that's not in this thesis that demonstrated that wasn't very effective at doing, but we're not going to talk about that too much today. Without knowing that, you can't really give them scenes or levels that are pertinent to their behavior. So revisiting this graph, if you remember at the very beginning of this thesis, we also asked, in addition to game mechanics, we asked, how do you identify play personas, right? So then we can generate tutorials for them. We developed a way to classify playstyle based on mechanics using concepts from game mechanic alignment theory. So now we're going to enter this last part of the thesis, play persona classification. And it's actually really, really simple. We trained a support vector machine classifier on that Mini Dungeons 2 data set, which I mentioned before, using mechanical frequency vectors as a representation for a play trace. So remember mechanical frequencies, the number of times that a mechanic is triggered during play. You can build a vector of these things. We have those labels already easily available to us because of our action agreement ratio labeling, the thing that took 7.5 hours. And we can use the player label as that output. In order to compare and see if this was a good representation, if we can use mechanical frequencies as a representation for a play trace, we then took an LSTM, a long short-term memory network, and we trained that on sequences of game states using a cropped sequence of game states, again with the same labels as before. And we also trained that on that data. That gave us actually really interesting, good results. So it turns out that no matter what representation that you use, you get about 70 to 73% error, 70 to 73% accuracy. 70% error would not be good. 73% accuracy when compared to action agreement labeling, which is the ground truth that we're going to take. So if you're using an LSTM or an SVM, it's pretty good, right? Now, interesting fact here, the LSTM takes about half an hour to train because it has all those game states. The SVM, on the other hand, takes 30 seconds. So it takes 30 seconds to train on 853 play traces, and it can classify in less than a second, which we expect because that's a really tiny representation, right? It can go really fast. But it took us 7.5 hours to build those labels. Imagine if you were to try to put this in an industrial application, right? Like Candy Crush, which has 13 million daily players. Even if you were to classify a play trace at 30 seconds, right? You had an agent play the level with a player's play trace and say, do you agree with this or not, right? In order to classify them. That means that you'd have to do 541.6 thousand traces in an hour or 4,513 every 30 seconds, which is a server farm just devoted to classifying your daily players, which is huge. That's expensive. Labeling takes a lot of time, and game states are greater than integer vectors, and game playing agents take longer than either of these two things in order to label. So there's an industrial need here for if you had a player that was playing a game, you would be able to quickly classify the way that they played, so you could immediately feed them the next couple of levels that would suit that particular play style. If they were playing like a treasure collector in this example, you could choose whether to give them scenes that allow them to play like a treasure collector that encourage that behavior, or if you were trying to engage them in other ways, you could give them scenes that would discourage treasure collector behavior. Wow, that was a lot. So that's the equivalent of 10 research papers. That's how you get from mechanics and end up with tutorials. I hope over the last 40 minutes, I think I'm at 39 minutes right now, I've demonstrated how you can generate tutorials and tutorial levels for video games using mechanics and play personas. But I want to leave with a couple of questions and challenges where I think this research could go next. The first is regarding mechanics. We've been using mechanic graphs in order to do critical mechanic discovery. It's kind of a requirement to search mechanic space, right? It's that abstraction that allows us to look into this. But how can you extract mechanic relationships without insider knowledge? The GBGAI framework gave us a lot of shortcuts because it uses a certain language called video game description language that allows you to understand the interworkings of a game. Maybe there's a way that we can do this rather than using VGDL. Maybe we can use video or an agent playthrough. Another is, how can we separate mistakes from player intent? Game mechanic alignment theory kind of assumes that a player meant to do something. And as a designer, you need to figure out, did a player mean to jump 50 times? Or were 45 of those times accidents because they couldn't figure out what the A button was doing and they didn't know which character they were on the screen, right? You're going to run into problems like that all the time. So we got around separating player mistakes and accidents and tried to lessen that noise by only using winning play traces in our study when we were looking at those game mechanic alignment, because the assumption is, well, first off, not many people lose mini dungeons. It's very simple. But also, when you look at winning, people typically intend to win games and they don't intend to lose them. So you're going to find a lot more mistakes in losing play traces than you will in winning ones. So there's some noise that you need to sort through there. The next is about personas. If you remember, persona dependent scene generation requires procedural personas to work. What happens if you don't have those, right? We've been actually exploring different ways to use Map Elite's neuroevolution to search for diversity of play style automatically using game playing agents and evolution. This is still work in progress, so I don't have any results to show you, but that is a research direction that I'd like to take this in the future. And then are there better ways that you could classify playstyle? We were using mechanical frequency vectors, maybe a different representation such as mechanical sequences. Maybe runners do things in a different order than a monster killer would or a treasure collector would. And lastly is with tutorials. I'd like to build mechanic discovery and GMA into a pipeline. We kind of did this with the Adelphi framework where we took uninformed mechanic discovery and shoved that into a tutorial generator for examples and instructions. But we don't have something yet that can go from mechanics all the way through to level generation, which would be a really, really cool, smooth way of doing this. Utilizing that information directly like in real time. And then the last question is, what games should we try this on? It works for games like Mini Dungeons 2 and Super Mario, but in the grand scheme, Super Mario and Mini Dungeons 2 are not very complicated games, right? BioShock, Civilization, Call of Duty, those are much more complicated games with much more interesting mechanic relationships going on. And that would be a real challenge that I'd like to overcome using these methods. And then to leave you guys with the final thoughts, what about domains outside of games? What about things like science or mathematics or even language? Students are people and people are unique. They learn at different paces and they gravitate towards topics that they enjoy learning. So imagine a world where students could receive a personalized education, like a truly personalized education that can adapt itself to the wants and needs of the student. My hope is that the ideas in this thesis may serve as part of a foundation for personalized learning. It's going to be a lot of work, but I'm looking forward to it. And that's it. That is my thesis.
Thank you, Mike.
I will stop sharing my screen now, and I guess people could unmute. Hi, welcome back.
All right, that's great. So now we take questions from the audience. Audience is both people in the room and in Zoom. We usually don't have questions from the thesis committee during this phase. They're allowed to ask questions during this phase, but we usually the committee will ask questions in the closed session. But we'll have about 10 minutes or so for like audience questions. Mm-hmm. You can either just speak up or like post it here in the chat.
Can they unmute themselves? Is that something we're allowed again?
Oh,
I think we'll allow you guys to unmute yourselves. So if you want to, don't everyone go at once though. That would be problematic.
I think I just asked them all to unmute.
Oops. All right, the floor is open.
But they should be able to. Yeah.
I have a question. I can get things started. So thanks and congratulations. And we should talk more about this mechanic discovery stuff at some point. But how do you think that your system would work on games that don't have really a reward signal, like something like Minecraft?
That's a really good question. So actually, okay, again, I didn't get to put everything into this thesis, but I'm so glad that you asked that. So in Minecraft, or like in The Sims, for example, you could invent as a designer or a player the types of goals that you want to achieve and use that as your winning condition. So for example, in Sims, it could be like getting the highest paying career path, or it could be, I don't know, like okay, this is really sick, but one of my favorite things to do in Sims was have all the different kinds of ghosts that you could have in the game, which involved, I guess, mass murder on a genocidal scale, like in different ways too. So that's kind of, sad, but, I was an interesting kid. Or like in Minecraft, it could be things like beating the Ender Dragon, which kind of serves as the end game. I think it's literally called the end, the place where you beat the Ender Dragon. But like, for example, in Minecraft, have never actually fought the Ender Dragon. I've never gone to the end. I've only built a bunch of cool stuff. So those would be more of a designer defined goal. Does that answer your question?
It does. I think it's one way. Without going on like a half an hour rant about the things that I would like to see in games, I'll just say, yes, that's fine. Let's talk more later.
Okay. Okay.
Nice. More questions?
Is it possible that we didn't see any levels where the runner is not the best choice?
Right.
Is there any situation in which the runner winds up screwing themselves over?
There are a couple of examples. So they were both in the paper and in the thesis. I wasn't able to bring them into this because they would have required more explaining into the idiosyncrasies of runners versus the other personas. So But in a nutshell, when the treasure collector has no more treasure to collect and the monster killer has no more monsters to slay, they act like runners. So it's very hard to deceive a runner without also deceiving one of these other two personas, which then take on runner heuristics after they're done with their primary objective. But there are a couple of levels where the layout is in such a particular way and the way that the agent's search is in such a particular way that if a runner goes straight to the exit from where they are, they will end up with lower health than if they first went outside of their way to get a first objective and then back to the exit. But I figured that would have been a little more challenging to explain. But yes, there are a couple of levels. They're rare, they're harder to find, but they do exist. Good question.
Can you
Yeah.
hear me, Mike?
Yes.
So you ended the talk talking about your ideas for use of this in education, and I was wondering because education has the problem that Lisa was describing is even bigger, right? How do you define the goals or the action sets or mechanics in, say, math or teaching a student English? So I just wanted to hear more of your vision of using this type of research for education.
Oh, that's good. That's good. So education is always this. So one of the reasons why I put that in as a stretch goal is because I believe that would be the penultimate stretch goal for this kind of research. I think that exploring other domains that do have predefined goals would be a clearer path forward because education can be so open-ended. And just like in something like The Sims, or I guess in Sim City, or basically a lot of simulation games, there are open-ended goals there that the player has to come up with themselves. So if we were talking about a truly personalized education, then the person would be able to come up with those goals themselves, right? And then the curriculum would adapt itself to what the player wanted to accomplish. So I can't say that there'd be one goal that would end all. So, like if I want to be a mathematician, then I'm going to have certain goals in my education versus someone who wants to be a novelist, right? There's just going to be different things that I want to accomplish there. So if we're talking about truly personalized education, I would say the user would come up with those goals themselves, and then the curriculum would adapt itself to the user. That's nothing concrete, and I don't have anything built like that yet. And just
that's why it's in the stretch goals. Thanks.
Exactly.
Right. Audience question?
As somebody who is not,
That's
not
okay.
live in this world,
That's fine.
maybe you've explained this, maybe it just went right over my head. But when you're talking about this, I know that your thesis is mainly on tutorial generation, but does this research go into, like, if, I know that I play games very different than Ahmed plays games. I like to explore a lot of things and find all the little secrets and things. Ahmed likes to get to an end and then go back and figure things out. Does this play into, like, how games can be designed for different players? So the entirety of the game kind of suits itself to my needs. And then Ahmed plays a completely different game and Widget plays a completely different game.
So that's really interesting because we are, in our research here, we were restricting ourselves to these simple levels. You see simplicity featured its way as the fitness function for the majority of the objective optimizations that we were trying to do here, right, as the fitness. So if you were to, instead of trying to optimize for simplicity, but optimize, say, for something like difficulty, then you'd be able to have bigger and bigger challenges that were maybe better suited for you. So we scoped ourselves to the beginning couple of levels that you would play, or trying to introduce certain behaviors to you to keep things simple. But it would theoretically be possible, I think, if you were to optimize for a different objective, like difficulty or I guess a targeted entropy. We were doing the simplest entropy that you possibly could for simplicity, but if you were looking for something more cluttered. In fact, Ahmed and I were actually doing research using a different agent, the A-star agents that were too good. Ahmed's familiar with this. And we accidentally on purpose, I don't know, we accidentally built these, like, in chess, how when you're studying chess, you get these like 10 moves to mate kind of thing. Well, these are like 25 moves to mate kind of puzzles. Like they were almost impossible to think through as a person, but an agent was able to think through them. And there was really only one or two correct solutions. So like if you wanted to target more difficult stuff to give yourself like a curriculum that slowly gets more difficult over time, but is personalized for you, I believe that's possible. But I think that's outside of the realm of tutorials, right?
Right.
We're not introducing things to you anymore. We're just challenging you at that point. Like,
yeah,
we out of time?
Oh, Philip, one of you.
Yeah.
Hi, Philip.
Hello. I'm far away across the river. So my question had to do with at the beginning of your talk, you mentioned, I think, like 3 types of tutorials. We call them, like one of them was textual instructions. And I was wondering if while you've been working on your PhD, all of these advances in natural language processing and like large language models have come out. And I wonder if you've put any thought going back into that with what that would allow
Yes.
for like instruction generations. Like, you have all this mechanic information, whether that could be like prompts for like a language model, or what do you think about that space?
So I was using a grammar tree because this was at the in my defense. This is my defense, but in my defense of myself, not my thesis. This was at the very beginning of my research. So grammar trees to me were the thing. And I think in 2016, we didn't have GPT-3. But yes, now that we've had advancements since then, I think that language models have unlocked a lot of capability for instruction demonstration. I think even GANs have unlocked a lot of capability, possibly for demonstration, right? Maybe we don't even have to have an agent play the game to capture these frames. Maybe you could just generate the visual itself. I don't know. Or, image generation with diffusion or something like that. I don't know. There's a lot of exciting advancements that could allow you on those first 2 types to do some cool stuff.
Cool.
Yeah.
If you have the data.
If you have the data.
Or pre-trained stuff to get away with it.
I think Ming had something as well.
Yeah, hi, Mike. I thought I'll type it just in case you hear some extra noise. My question was more on a more abstract level in terms of like you have mechanisms for finding critical paths and branches that leads to, for example, generation of the tutorial for a game, right? Have you thought about using a similar approach to maybe automated code generation, whereas you're given a specific goal, code paths and branches can also be generated using a similar fashion?
I haven't actually thought about that. No, that's a really interesting concept. So we should definitely talk about this offline. I'd be curious as to your thoughts about that.
Okay, I think we have reached the end of the open part. So we're going to have to ask those of you who are in the room to please wait till we get out of here. Please wait back in the lab.
I'm going to stop recording.